Hello and welcome to today's session in the complementary series of webinars provided by Sartorius Stadium Data Analytics AB. My name is Lennart Eriksson, and as you may have observed, the old Umetrics business are now part of Sartorius Stadium Biotech. The roots of our business go all the way back to 1987 when Professor Svante Wold and Rolf Karlsson founded a small company located in northern Sweden, initially called Umetrics AB, which later on became Umetrics, and these days we are Sartorius Stadium Data Analytics AB. We are a business solution provider in the fields of advanced data analytics, and our solutions are realized through the so-called Umetrics Suite of data analytics solutions. This suite comprises the model software for design of experiments and quality by design. We have the easy analytics software for enabling everyday data-driven decisions in an efficient way. We have the SIMCA offline software, which will also be in the focus of today's presentation. And many of the models that are calculated and built with the SIMCA offline software can then be used in a more online context using the accompanying tools SIMCA Online, Control Advisor, and Active Dashboard. We have a series of dedicated webinars going through the analytical powers of the Umetrics Suite of data analytics solutions, so I will refer to those recordings for going through SIMCA Online, Control Advisor, and Active Dashboard. The mission of the data analytics business of Sartorius Stadium is that we are trying to drive growth by enabling our customers to see what others don't, and our vision is that we want to be recognized as the leading data analytics solution provider. Here we see a little overview of today's presentation. We have an introductory section. We will discuss data analytical tools for different data analytical objectives. Gradually then zooming in on OPLS, and we will present some examples, and OPLS, where we will also present some examples. The final part of this presentation is a software demo, and in this demonstration we will target the OPLS method with one of the examples that we are discussing. And finally, as I told you, there will also be a Q&A session. So as an introduction to today's presentation, we can say that we find ourselves in a numerical jungle because more data than ever are measured, and one of the investigations that we are often departing from in our argumentation is an estimate made by the UNICE, the United Nations Economic Commission for Europe, that late 2015 made an estimate that within 3 to 4 years' time, counted from 2015, the amount of expected data was estimated to treble. So our conclusion is that data is found everywhere, from the production floor to the local grocery store and even Facebook. And the question is, how do we get value from the heaps of data? How do we find out in which direction for move for improving the result? How do we extract and cultivate the golden nugget that may be found in our data? Well, fortunately, the SIMCA software has a number of data analytical tools that can help us to extract the information out of these heaps of data. And in the initial part of this presentation, I will spend 2 slides going over the available data analytical tools, and I will do so using a process data analytics perspective. But of course these tools also apply to other types of data, for instance data coming from the financial sector, omics data, spectral data, and other similar multidimensional data. Regardless of what type of data you are working with, the mother method is called principal component analysis, or PCA for short. PCA is a tool that is used to summarize and visualize the information in one data table, and in our notation this is often called the X matrix. And in the process modeling context, this would then be a block of process input data. So with PCA you can build a process monitoring model that will help you and tell you whether the current process condition conforms well or not at all with what was good conditions in the past. So one of the main objectives is to extract a model that is capable of distinguishing good from bad, and also can help you to extract early warnings or disturbances or deviations from good operating conditions. And when you have a hiccup, preferably it should also be possible to find the so-called assignable causes, which means to be able to interpret and understand why deviations occur, and perhaps also in the long run to avoid these issues in the future. Sometimes you have a second block of data available, and we can call this block of data for process outputs. The process output block is sometimes just one single process variable, a process quality or a throughput, whereas in many other cases it can really be a matrix consisting of several variables, for instance qualities, yields, throughputs, and so on. In this case, in this scenario, you have a slightly higher ambition level from the data analytical perspective, you can say, and you want to try to find out the information overlap between the process inputs and the process outputs. You want to be able to use a regression model or calculate a regression model that can link the systematic variation in these two blocks to each other. And when you have that data analytical objective, you're looking into regression extensions of PCA. In the Simca software, we have two regression extensions. We have PLS, which is an acronym for partial least squares, and we have a variant of PLS called orthogonal PLS, OPLS. So with these two tools, you're looking for the information overlap between the process inputs and the process outputs. And the hope or expectation is then that by measuring equivalent process inputs for future time points or additional samples, you will be able to reliably and consistently over time predict the process qualities for these future time points or future samples. The two tools that I mentioned now, PLS and OPLS, they are also used in another context, process modeling context, where you have a slightly more elaborate architecture of the process data. And here I'm thinking of the batch process data that are available. So when you're modeling or working with batch processes, you have two types of process inputs. You have first of all what we call the initial conditions, which is a two-way data table where for every batch that you're going to launch, you have one or more measurements reflecting the initial configuration before starting the batch. Then the second type of process input block is not a two-way block but a three-way block where each batch can be seen as a layer or a sheet in the three-dimensional data structure. And these are the batch evolution measurements. These are the process measurements and perhaps spectroscopic measurements and in-process control data that are measured during the batch evolution, sometimes with high frequency and sometimes measured with a slightly less tight frequency. Regardless of how the data blocks are, how many variables you have in the different data blocks, it is still the same sort of objective. You want to link the information in the process inputs to the process outputs, trying to understand how initial conditions and the batch evolution measurements correlate with the final qualities. So PCA, PLS, and OPLS can be said to address these data analytical objectives that we have been talking about. And just for a little recap, the data analytical objectives we are referring to are an initial data overview, a summary. It can then be classification, discrimination, regression, and prediction. Now, in more recent years, we have seen the emergence of a new data analytical objective, which we call data integration. In the literature, it is also sometimes understood as data fusion. data integration or data fusion is of interest when you have 2 or more blocks of data where you do not necessarily want to regress one block of data onto the other, but the goal is rather that you want to compare the blocks and find out what information they have in common, and also find out what sort of information is unique, what is only confined to a certain data set, and it can't be found in any other data set or data block. The SIMCA software already today is equipped with one of these data analytical tools, which is the OPLS method, and it has the objective to summarize, quantify, and visualize the information overlap between 2 sets of data. And if you're then using OPLS together with the rather flexible implementation of hierarchical modeling that exists in SIMCA, you can address almost any number of data blocks already today. Interestingly, there is also an ongoing academic development regarding a technology that is called ONPLS, where the lowercase n means any number of data blocks 3 and 4 and higher. So ONPLS involves the integrated analysis of any number of data sets, and we here visualize its properties using 3 data blocks that we are calling X1, X2, and X3. And this integrated data analysis means you will have a model with many different compartments, and each compartment then carries or encodes valuable information. And first of all, the model will have components reflecting what is called globally joint information. It means information or structure that is present in all the data blocks that you are modeling. And then we have the locally joint information that is found in at least 2 blocks, over to the unique information that is only found in one of the data blocks. And of course, you will also have the residual structure that represents the unmodeled variation. Now, with this little introduction in mind, we are now moving over to the 2 tools that are forming the basis for today's presentation. First of all, we're going to discuss the OPLS tool and look at some examples. The usual way for us to introduce or position OPLS is to compare it with PLS for the single Y scenario. And one way to understand what OPLS is that it is a rotation or a transformation of the conventional PLS solution. I want to emphasize that if you have an OPLS model and a PLS model for the single Y situation and with the same number of components, they are completely equivalent. They have the same predictive power. To the left, we see a PLS score plot for a multivariate calibration example where the samples are colored according to the changing content of the analyte of interest, and where blue means a low content of the analyte of interest and red color means a high content. And we can see that according to the arrow, that is how the 2 first components of the PLS model will capture the systematic changing analyte levels among the samples underpinning this multivariate calibration model. In the right-hand part, we see a similar score plot developed for the OPLS model, and we can see how a rotation has taken place such that the predictively interesting information is now zoomed into or focused into the first component only. So when we are going from left to right in the horizontal direction, it corresponds to increasing contents or levels of the analyte of interest. And that also has a consequence that when we want to interpret which spectral features in the measured data correlate with the changing proportion or levels of the analyte of interest, we only have to look at the loading of one model component. And that is why we prefer OPLS over PLS for interpretation. Here we have another way trying to contrast PLS and OPLS, and to the left we have the situation for PLS and the variability occurring in the X block. So PLS will divide the variability in the X matrix in 2 parts. the systematic variability, which is the green color, which we denote R square X, and the residual variability, the unmodeled variability, which we call E, and it is from this residual information we are computing a very important model diagnostic statistic that we call D mod X. OPLS is then able to further split this systematic variability in two parts. The part that is linearly correlated or predictive to the Y, and the part that is uncorrelated to the Y but still systematic variation among the samples. If we zoom in on the OPLS model structure for the single Y situation, this ability of OPLS to partition the X information in two parts means we get two types of components in the OPLS model. We will have, for the single Y situation, always only one predictive component, which will have a score vector T on the X side and a score vector U on the Y side. We will have a loading vector for the predictive component where the loadings are called P, and on the Y side we will have just one single loading element which we call Q, one element just because we have one single Y variable. In addition, we have these components that summarize, capture, summarize, and visualize the orthogonal variability in the X block. Information in the X block that is systematically changing between the samples, but which is uncorrelated to the Y variable. And here we have depicted that part of the model as matrices because we can have 0, 1, 2, too many of these orthogonal components. One of the arising or emerging uses of OPLS is in the modeling of batch data, and we are now going to review a little study that we made 2 years ago on a batch hydrogenation reaction dataset where PLS and OPLS were compared as far as their performance for batch evolution modeling. The initial feeling we were having is that because PLS will maximize the covariance between X and Y, there is a risk that undesired systematic variability among the process variables can be picked up by these batch evolution models in terms of more components and then meaning more control charts to monitor. Whereas the hope or the anticipation was perhaps that because PLS is able to divide the systematic variability in X in two parts, the predictive and orthogonal parts, this would perhaps affect how the score trajectories are estimated and the associated confidence intervals around these score vectors. A little more detail on this example. It is a conversion reaction where nitrobenzene is converted into aniline in order to get some variability in these batch reactions. A DOE was used in two critical parameters. It is a reaction temperature and the initial concentration of one of the reactants. The DOE was set up so that it had 6 center points encoding a normal operating condition, and then there is the regular DOE array of 4 outer experiments, and in addition to these 4 outer experiments there were also 2 other additional process disturbance batches with more deliberate and more perhaps non-common changes induced. So the 6 center point batches were used to encode knock conditions, and they were used for model training. In order to monitor the progression of the reaction, spectroscopic measurements were done in the 200 to 300 nanometer spectral window, and the spectra that we are using in the analysis have also been pre-processed, taking the first derivative. In addition, there are 7 process variables: the reactor temperature and pressure, gas feed, jacket in and jacket out temperatures, flow rate of oil, and stirrer speed, and this is the original literature reference. So the way we are now unfolding the three-way batch data structure is as follows. We will use the data for one batch after the other in this sequence. So the first top row is the first time point of the first batch, and then all the measurements down until the last time point of the first batch. And then we start with the data for the second batch and so on. We are using the measurement time as a Y variable to give the model a direction. We need not necessarily use measurement time if we have some characteristic variable that is indicative of the batch progression or batch age. We would call such a variable a maturity variable. We could use that instead of a time variable. But in this example, we are using time. So we will use the 6 normal operating condition batches and develop one PLS model and one OPLS model. And on this slide, we see the control charts arising from modeling the 6 NOC batches. We can see that, or perhaps we should walk through the common building blocks of a control chart like this. So the horizontal dimension corresponds to the batch lifetime from 0 minute up to 45 minutes. The green dashed line, that is the average of the 6 normal operating condition batches, and the lower and upper red dashed lines correspond to the plus minus 3 standard deviations, and the solid line is then one of the batches, how it has evolved. We can see that for the first batch, it is of course inside it's the limits of the control chart both for PLS and OPLS, but it's definitely so that there are tighter limits around the score in the score control chart arising from the OPLS model. We will now show results for 2 of these test set batches. We start by displaying the batch that had the high combination, high temperature and high initial concentration. This is a very fast batch producing a high amount of product. We can see that OPLS consistently shows this difference in the score plot, whereas the PLS model would suggest that up to at least 10 minutes, this very fast and high amount of product batch is still rather well aligned with the normal operating conditions. So PLS is not as sharp and capable, you can say. The second example is another of the outer points in the DOE. This one has a low temperature and a high initial concentration. This is a batch where the reaction is slow and it produces a low amount of product. We can see that OPLS consistently shows this difference in the score plot, whereas for a good almost 2/3 of the duration of this batch, the PLS model would suggest that this slow batch actually conforms very well with the normal operating condition. And the conclusion here, or the insight here, is that this ability of OPLS to separate predictive and orthogonal variabilities leads forward to control charts that are more precise and more where the control limits are more well defined. Other applications of OPLS is in multivariate calibration. Here we have just another example for the single Y scenario where OPLS seen to the right is able to enrich the predictively meaningful information into the first component. OPLS is also used a lot in omics studies, and particularly the so-called discriminant analysis extension, OPLS-DA. With the SIMCA software, we have a dedicated user interface for people that have omics data. We call it the omics skin. There is a separate webinar on the omics skin. The omics skin has an analysis wizard, which is represents a guided workflow to help people analyze the data and perhaps also avoid overlooking critical steps. And we see a screenshot here of one of the popular views inside this analysis wizard of the skin. And at the end, there is also a reporting tool with specific omics templates that facilitate documentation and reporting and communication of the models. We will now go over to the OPLS method and some examples. But first we have a little more introductory type of consideration. We are going back to the PLS and OPLS again because there is an interesting thing here that I want or an interesting message I would like to convey. And when you are using PLS and OPLS, you can say you are silently assuming or silently implying that the information flow is from X to Y. So in the prediction sense, X always gives Y. So in the prediction sense, you can say that or argue that PLS and OPLS are unidirectional. And that is how you would like things to work in the regression situation, because you would measure additional X for future sample and you want to predict the Y then for the future samples. In the integration or data fusion situation, there is another relationship between X and Y, because here information can flow in both directions. The OPLS method is symmetrical in the prediction sense, because not only can X be used to predict Y, but the opposite is also true. You can use Y to predict X. And so the two here in the name arises from this bidirectionality, not that it has two blocks or anything else. For OPLS, it is the bidirectionality that is the original reason for the naming OPLS. This bidirectionality means that you will have a model of three compartments. You will have components that express the information overlap, which we would call the joint information. You will have components that express the information that is unique to X, and components that express the information that is unique to Y. So once again, a little recap of PLS and OPLS, the regression problem. Here, the preferred language talks about predictive and orthogonal variabilities, whereas in the data integration or data fusion scenario, we recommend a switch in the preferred terminology to emphasize that data integration and data fusion has objectives that are different from regression. So rather than talking about predictive and orthogonal variabilities, we prefer to talk about joint and unique variabilities. So the joint variation is information that is found in all blocks, and the unique variation is, well, obviously something that is confined to just one of the two blocks of data. With OPLS as it is implemented in the SEMCA software also comes a modified overview plot. We have an OPLS overview plot that is dedicated to display the different types of components that comes with this model. And here you see on this slide this overview plot, and it is a conceptualization or realization of this concept. So it's a more detailed version of what we were looking at on the foregoing slide. The interesting thing with this overview plot is that it is stacked, it is segmented, you can say, and color-coded to indicate the magnitudes of the joint and the unique variabilities. And this segmenting means that if you click in any segment, you will open up the corresponding score plot. I will show that also in the demo that will come later on. Because of this bidirectionality and because you can have many more Y variables than just one in the Y block, you will have a more elaborate model structure. So we recognize this part from the OPLS model, the components that capture and express the joint information, the overlap. We also recognize this part, the orthogonal in X components, that expresses variation that is unique to X. But the additional little element is now the orthogonal in Y components that will then express information that is only found in the Y block. There is you can say regarding these orthogonal components, there are some of those components are estimated by the OPLS algorithm, but then there is also a final PCA step that takes on after the convergence of the OPLS algorithm. So we have a separate PCA step to fully exhaust the residual variation on the X side, and also to fully exhaust the residual variation on the Y side. And if you look very carefully at the OPLS overview plot that I was showing 2 slides ago, there are different colorings in the orthogonal in X and orthogonal in Y parts of this plot, and that coloring is used to indicate the estimation principle for the orthogonal components, whether they were estimated as part of the OPLS algorithm or the late ensuing PCA step after the convergence of the OPLS algorithm. And the origin of these orthogonal components is also indicated in the name of the components in the model window that we will come back to. A couple of examples. We have the batch hydrogenation dataset that we again can analyze and illustrate this data analytical tool, which we will do, and this is what we will demonstrate. But we will be doing the data analysis detached from the batch modeling. We would just analyze the data without really considering the batch nature. So in the what we will do here is that we will have the spectral information, the 80 spectral variables as an X block, and the 7 process variables as a Y block, and try to find the information overlap, if there is any information overlap between the 2 blocks. And the expectations is that the measured spectral data will very closely follow the progression of the conversion reaction. They will be very indicative of the chemistry, we can say. And the question is how indicative the process variables will be of the progression of the reaction, how indicative they are of the chemistry that is taking place. When we apply OPLS to this data set, a model with 9 components results. It is using the notation of the Simca software, a 1 + 6 + 2 component model. The first number here, the 1, means we have 1 single predictive component. 6 means we have 6 orthogonal in X components, and we have 2 orthogonal in Y components. So the first single predictive component will express the information overlap between the spectral data and the process data. The 6 orthogonal in X components will summarize additional variation in the spectral data not found in the process data, and the 2 orthogonal in Y components will summarize additional information in the process measurements not found in the spectral measurements. And you can see now how we have compartmentalized the model window to indicate these different types of components. And as I told you, in the name of the orthogonal components, we will indicate whether it is a PCA estimation principle or part of the OPLS algorithm. In this case, all the orthogonal components were estimated as part of the OPLS and OPLS algorithm. There are no orthogonal components arising from a late PCA stage. We can look at the single predictive component. Because it's just one component, we can look at the loading in terms of a loading spectrum to look at the NIR loading profile, and we can look at the Y-side loading in terms of a column plot where we also see the confidence intervals. So now we're looking at the information overlap between the spectral data and the process data, and because we are aware of the fact that the spectral data are very closely adhered to the chemistry, then whatever we see here in the loading plot on the process side, on the Y side, would be process parameters that have a high impact on the chemistry and parameters having no impact on the chemistry. So Reactor temperature and gas feed, these two are very critical quality parameters. They have a consistent effect on the chemistry, whereas, for instance, reactor pressure and stirrer speed have no or comparatively little influence on the progression of the chemical reaction. We will come back to more details of this data set because it is the one we will be demonstrating. There are several other types of applications where OPLS has found use. You can compare multiple analytical measurements that are run on the same set of samples. One very interesting application that I've seen in the literature is where you have a set of spectra, original spectra, making up an X matrix, and then you apply some sort of spectral filter on these spectra, a derivation or an SNV or some wavelet compression or whatever. And then that will form the Y block, and then you can compare the X and Y using the OPLS tool to find out if you're inducing some systematic variations to the filtered spectra following the spectral preprocessing technology that you are using. On the other hand, if you have a very high overlap in terms of the joint variabilities, then you're not inducing other systematic variations among the spectra. And there are many other different types of application areas that are conceivable. Finally, I also want to have a little word on the omics side, where OPLS has been used in a systems biology study. In this example, data that we are referring to is part of a wider set of studies made on atherosclerosis drug trials on a certain strain of mice. There were one group of control animals, one group undergoing a low cholesterol diet, and one group of samples coming out of animals undergoing a high cholesterol diet. And then there were also differences, different blocks of the variables, lipidomics and free fatty acids. And in a publication that was published in Analytical Chemistry 2 or 3 years ago, they outline a work approach consisting of 5 steps, how to use multivariate data analysis in systems biology. And they have an overview step, a yardstick step, a predictive analysis and exploratory step, model comparison step, and then finally a biological interpretation step. And this workflow is based on combinatorial usages of both PCA and OPLS and PLS and OPLS discriminant analysis in different combinations. Here we see an overview of the available data structures or data sets. You have the control group, that is the top row. You have the low cholesterol diet fed rats, which is mice, which is the middle section, and then you have also the high cholesterol group. You have different blocks of variables, and depending on what you're looking for, if you're looking for variable information overlap in the different variables, or if you're contrasting different classes of samples with each other, you would work with different types of data analytical engines. So I will refer to this publication for a very, very interesting discussion on the use of OPLS in systems biology. This brings us over to the demonstration, and I will now go into the SIMCA software. We will be using this batch hydrogenation dataset to illustrate the OPLS. So first of all, we will define a new project. We will locate the dataset, and the dataset is stored in an XLS file. We have one worksheet for the UV spectra, the ultraviolet spectra, and one worksheet where we have the process parameters. So we will import them as separate sheets. We will have one sheet for the process parameters and one sheet for the spectral data. Those of you that have attended other recorded webinars will know that SIMCA operates on the principles of primary identifiers and secondary identifiers. for the rows and the columns. So the primary identifier is the plot label or plot mark that will always first be thrown up in any plot or any table regarding samples and or variables. And then you can have additional secondary identifiers for encoding sample belonging or metadata information and so on and so forth. The process parameters are Y data, so we have to tell Simca that these are Y variables. If we are not saying anything, Simca will silently assume that all variables are of the X type. In the bottom part, of the import routine, we have this issues pane, and it reports no problem. So we can finish the import. We can overwrite an existing file already because I did a little rehearsal of this a couple of hours ago. So now we are inside main Simca, and we will have two data sets that have been imported. We can always choose to open the data sets just to, so to say, verify that the import seems to have completed in the expected way. And we can also look at the process parameters. If we are working with spectral data, Simca has a very handy way, a handy tool, or a tool for handy plotting of spectra that is under the data tab using the spectra button. And here we see the different spectra in the used wavelength interval. These are then first derivative pretreated spectra, I should also say. So this is one way to visualize the data. You can of course also visualize the process data, but they are not as exciting, you can say. We are going to have to tell Simca from the imported data what sort of subset of data we would like to base the model on. So we will have to specify a work set coming out of the imported data sets. We will have a model that includes both X and Y, and then we have the overview tab to see all the samples and all the variables. One little modification that I will do from the default setting is regards the scaling of the spectral variables. I will not want to use them for unit variance scaled in the unit variance scaled mode. I will want to have them only centered because that is the usual way to pre-process variables that have the same numerical range and same mechanism or generation principle behind them. Whereas for the process measurements, they have very fundamentally different standard deviations. It makes much more sense to use the unit variance scaling principle, which is the default in Simca. We will now be using an OPLS model, so upon clicking OK and exiting the workset dialog, we have prepared for an OPLS model. We use the AutoFit tool to calculate a model, and we will then see, if we open up the model window, this compartmentalization of the model window corresponding to the different types of components. We can then see, for instance, that the information overlap is such that 75% of the variation in the spectra overlap with 39% of the variation in the process measurement. So this is what you would expect, a rather high fraction of explained variance for the spectral variables in the predictive component or the information overlap component because the spectra are so closely reflecting the chemistry and the progression of the reaction. We can also choose to plot these data in terms of this dedicated overview plot rather than to visualize them in the model window. So here we have arranged or tiled the model window and the overview plot side by side, and the sizes of the green fields then correspond to the information overlap. So 75.6% of the variation in the spectral measurement overlap with 39.4% of the variation in the process measurements. I will just show you how you can click and this clickability of the OPLS overview plot, and that you will directly go into the corresponding score plot. Here we see a worm-like structure to the scores, and that arises because of this autocorrelated nature of the observations. The adjacent time points are very correlated in batch modeling, and that is why you have these worm-like structures. So each worm corresponds to one of the 6 normal operating condition batches. Because we have this time ordering, the preferred score plot representation would be a line plot rather than a scatter plot. And whenever you have a model with many compartments and components, you will have a score plot gallery and also a loading plot gallery from which to select more selectively what type of plot you would like to investigate. The default action is always a scatter plot. So we can, for instance, choose a line plot. We will then be looking at the score vector of the predictive component. We can also color this one according to the identifier. We have an identifier corresponding to the 6 different center points, so we can see. So now we have a color coding showing us the observations or samples of the different batches. So here we are looking at changes in the spectral measurements in the information overlap. So we can see we have an initialization part, and then we have a sharp turn here coming to the whether a conversion reaction is really taking place, over to an end where we have a completion stage, and then comes the second batch and so on. We can now plot the loading for this component. Then I go to the loading plot and select the line plot. Now the default action for SIMCA is that it will always plot both the X loading, which is called P, and the loading, Y loading, which is called Q, side by side. Now if I want to zoom in on the spectral part, the X loading, which is called P, I will have to remove the Q loading, which corresponds to the Y part, the process measurement. So I will select only the P loading now, and then we can see the loading profile corresponding to how the influences of the spectral data are or is in this first model component. We can also plot that plot, of course, with the using the wavelength information. Of course, I could have done that. So we see also the wavelength information here. Okay, let's close a couple of plots here. It becomes a little crowded. We can continue with the score line plot. Now instead of plotting the X score, we can plot the U score on the Y side and see how things are evolving in the information overlapping among the process measurements. So now we're looking at how the information overlap is, what information in the process variables follow the chemistry, and you can see there is a more extreme and a little wiggled, sometimes a little erratic pattern, you can say, to these scores. Now we can, of course, then also look at the loading for this component. Now, because we are now going to look at the process variables, they don't have any real spectral association with them. We could instead choose to plot the column plot and now remove the X loading P and only look at the Y loading Q. So here we see how the different process measurements contribute to the information overlap, and we see we have a large loading for reactor temperature and gas feed. So variations in these two parameters has a strong influence or a strong connection to how the chemistry is evolving. Whereas, for instance, stirrer speed has a very small loading, so variation in stirrer speed is not really following the chemistry of the reaction. So now that we have looked at the information overlap, we can go in and start to look at the unique variations that is confined to just one of the blocks. And it's very easy to do. We're just selecting TO, we are now looking at an orthogonal in X component, the score for the first component, and this is about 7% of the variation in the X block. So in these 7%, we see that there are actually some subtle differences between a couple of the batches. We have the batch CP2 that is moving slightly faster than most of the other normal operating condition batches, and we have a little indication that the batch CP5 is actually progressing a little slower than the other normal operating condition batches. And we can go in and look at the loadings and try to figure out why this is arising. In a similar way, we can also look at the unique information on the Y side in the process measurement. So now we're looking at changes in the process parameters. This is about 28%. We are looking at systematic variabilities in the 7 process variables, but that is not found or not contained in the spectral measurements. And here you see much more dramatic changes and more erratic behaviors. And by plotting the loadings of this component, we would again choose the column plot representation. We can look into, we will plot the loading Q because we are looking into process measurements, the Y part of the data, and for an orthogonal component we have to have the index O. So QO means we are now looking at systematic changes in the process measurements which has very little connection to the chemistry, and we see stirrer speed and reactor pressure, for instance. So here we can look at variation in reactor pressure that is occurring between these batches, but variation that is not connected to how the reaction is progressing. And you can go on and interpret scores and loadings for all the other all the other components in this model. So the basic and take-home message is that OPLS will compare the information overlap in 2 data tables, and it will either display that information in terms of a dedicated overview plot or as part of a tabulated summary in the model window. I think this is how far I wanted to drive the demonstration, so I think I will go back to the PowerPoint with just a few rounding off remarks. So we have been looking into the SIMCA software and its primary tool for data fusion and data integration, the OPLS. If you would like to see more of the capabilities of the Umetrics Suite and how it can help the users to see what others don't, we have a series of dedicated webinars for walking through. Removing the, you can say, software information and zooming in more on the data analytical result, you can say that the Umetrics Suite of data analytics solutions help you to investigate and answer these 4 primary questions that are brought forward by the Gartner report last year, the descriptive, diagnostic, predictive, and prescriptive data analytical objectives. So we can, with this tool set, find out what has happened. We can try to understand why did it happen. We can be more proactive and try to figure out what could happen in the future. We can also have the prescriptive mindset and try to figure out what should we do in order to get something to happen, or perhaps more importantly, what should we do to avoid things to happen. So with the Umetrics Suite, what we would like our users to be able to do is to understand how to capitalize on their data, understand what are the golden nuggets, understand how to work with them, understand how to change a little and thereby grow a lot. Having said that, I would like to thank you all for your time and attention, and I will be very shortly back trying to address your questions. So thank you so much for your attention.